Alright, so for example number 3, find the 10th degree Maclaurin polynomial for f of x equals cosine x. Use this polynomial to approximate the value of cosine of 0.5 and then compare it to the actual value. Alright, so yes, when you read this problem 10th degree, does that mean 10 derivatives? Well, potentially. However, we will find a pattern here that will simplify our work for a lot. You'll see. So we won't need to find 10 derivatives per se. So you will see. So number 1, let's start with f of x equals to cosine x. Evaluate f of where are we going to center our value? Yes, if you're guessing, you guessed it well, because if we're looking for a Maclaurin polynomial, that means it has to be centered at centered at 0. So we need to evaluate this function and its derivative at 0. Cosine of 0 equals 1. Find the derivative of cosine, which is negative sine, and evaluate the derivative. Evaluate the first derivative at 1. I mean at 0, rather, not at 1. That's a negative sine of 0, which is 0. Find the second derivative. That's negative cosine. Second derivative, evaluated at 0, negative cosine of 0, which is in this case negative 1. F triple prime, that's the derivative of cosine, which is negative sine times the negative is positive sine. And F triple prime, evaluated at 0, that's sine of 0, which is 0. Okay, let's take the fourth derivative. What's the derivative of sine? F triple prime, or rather quadruple prime, cosine of x. And the fourth derivative at 0 is cosine of 0, which is 1. Alright? Okay, so do we really need to take the fifth derivative? Okay, think about the following. So recall that these trigonometric functions are circular functions, because they come from the unit circle. You go around the circle, you go back to the same value, and check this cosine, and then cosine again. If we take the fifth derivative, we're going to get negative sine, which is 0. The sixth derivative, which is the same as the second. The seventh derivative, which is the same as the third one, and so on and so forth. So from here, I think this is enough to see the pattern. We don't need to find 10 derivatives, you'll see. So let's state in general what we want to find. Let's state the Taylor polynomial. It's a Maclaurin piece of n. In general, I know we're looking for the 10th one, but for now we're going to set up the nth one, and then we're going to truncate that polynomial to the 10th degree. You'll see. So that'll be, in the first instance, f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 x minus 0 squared over 2 factorial plus f triple prime 0 x minus 0 cubed over 3 factorial plus f to f quadruple prime x minus 0 to the 4th over 4 factorial plus dot dot dot. That means it goes on forever, and well, maybe not forever, n terms. Potentially infinitely many, but not for now. So in this case, let's plug in let's evaluate to the fourth derivative. so p sub n equals, so f of 0, which is 1, plus the first derivative evaluated at 0 was 0, x minus 0, and then minus 1, because the second derivative at 0 is negative 1, x minus 0 squared over 2 factorial, plus triple prime evaluated at 0, which is 0, x minus 0 cubed over 3 factorial, plus quadruple prime evaluated at 0, which is 1, times x minus 0 to the 4th power over 4 factorial, minus dot dot dot, that goes on forever in this case, right? So well, let's simplify this, and I would like you to see a pattern right here. See how the terms with the odd exponent cancel out because of the coefficient 0. I'm talking about this one, that one, and it would happen the same to the 5th degree, the 7th degree, the 9th degree, and so on and so forth. Well, so let's see what are we going to be left with when we see this. So p sub n equals 1 minus, okay, x minus 0 is simply x squared over 2 factorial. Let's leave it as a 2 factorial for now, plus 1 times x minus 0, that's just x to the 4th power over 4 factorial. Well, did you see the pattern here? And notice how we have positive, negative, positive, then another negative, then another positive, and then another negative, and then another positive, etc. So that'll be and also look at the denominator, 0 factorial, 2 factorial, 4 factorial. Do you see the pattern here? Isn't it the factorial of even numbers? How about 6 factorial, 8 factorial, 10 factorial, 12 factorial, 14 factorial, and so on and so forth. And x likewise, the same values, the same powers as in the factorials. Alright, so this would be the polynomial for cosine. However, well, this is n, and notice I'm denoting that n-ness with these 3 dots right here that denote that it continues for more terms. However, we are only interested in the 10th degree polynomial, so let's just write it down. So p sub 10 then will be 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10 over 10 factorial. Alright, so that's our 10th degree polynomial for cosine. Yes, technically I should have used a different color here. Okay, let me fix this. Let me fix this real quick, and then we go back to the problem. So now we are going to use this approximation to find to approximate another value. I believe it's cosine of 0.5. So for cosine of 0.5, we're again, just like we did before, we will just plug in x equals 0.5. All right. So let's see. So approximate cosine of 0.5. That is p sub 10 of 0.5 equals 1 minus 0.5 squared over 2 factorial plus 0.5 to the 4th over 4 factorial minus 0.5 to the 6th over 6 factorial plus 0.5 to the 8th over 8 factorial minus 0.5 to the 10th over 10 factorial. And while using a calculator, actually this approximation, the 10th degree approximation, is going to do a really good job, and this is approximately 0.878. Both approximation and actual. All right, let's do another one. Let's do another exercise. Let's find the 9th degree Maclaurin polynomial for f of x equals sine of x. All right, so I mean, let's take a different approach for this exercise, and keep in mind instead of finding 4 derivatives and writing a polynomial, let's take advantage of the previous result to and use that information to come up with a Maclaurin polynomial for this function sine x. All right, okay, we got a result for cosine in the previous exercise. We can get a polynomial for sine x if we take negative the derivative with respect x of cosine. All right, because the derivative of cosine is negative sine, but we don't want negative sine, we want sine, so that's why we multiply by negative. And if we replace ddx with the approximation that we got from before, that's let me see if I can copy and paste this. I'm pretty sure I can. Let's see, instead of typing it or rewriting it rather, so let me see if I can just paste it here. Nope, not possible. Anyway, I wanted to just copy and paste. I know it's possible, but for whatever reason it didn't work. Oh, I know I don't know why it's not working. Okay. Okay, perfect. It's pasted, but not what I wanted. Never mind. So I will just write it down again. Yeah, I wanted to save some time, but it didn't work. So this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial. Alright, so let's take the derivative of this right here. So take the derivative of each individual term. So let me keep this negative in front and take the derivative of 1, which is 0. The derivative of 2x, or x squared, that's minus 2x over 2 factorial plus 4x cubed over 4 factorial minus 6x to the 5th over 6 factorial plus 8x to the 7th over 8 factorial minus 10x to the 9th over 10 factorial. So let's simplify this, and okay, in the same way that we did before, with simplifying factorials without using the calculator. Okay, these 2 factorial, it's the same as 2 times 1, 4 times 3 factorial, or if you want 1 factorial, 6 times 5 factorial, 8 times 7 factorial, 10 times 9 factorial, and so on and so forth. Okay. So notice right here how these coefficients are going to cancel, the ones I'm highlighting, simplifying our result a lot better. Okay, at the same time, well, no, I'd rather do one thing at a time, never mind. So this is going to be negative 2 over 2, okay, those cancel, x over 1 factorial, and plus x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7th over 7 factorial minus x to the 9th over 9 factorial. Alright, and well, let's use this negative to simplify all this, no? So in this case, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Alright, so that's our piece of 9 of x. Okay, that's our piece of 9. And of course, they're asking us as well to find an approximation for this polynomial at negative 0.5. So in this case, sine of negative 0.5 on both the approximation and the actual, it's going to be negative 0.479. And of course, we get this value by plugging in this negative 0.5 wherever we see the letter x on the polynomial, and then, well, of course, use a calculator to simplify that, and then compare with the actual one by computing this on the graphing calculator. All right. So one thing too that you might have realized here is how the polynomial for sine. Okay, let me highlight here using different colors. Okay, we use a different color here. So for sine, what do we have? Do you see how we have all the odd powers right here? 1, 3, 5, 7, 9, and same for the factorials. In comparison with the cosine function, what did we get for the cosine function? Well, for that we got 2, 4, 6, 8, 10, same for the factorials. And let's have a look at the parity of these functions. So the powers and the factorials on the cosine function are all even, whilst for the one for the sine functions, they're all odd. And this comes from the fact that the sine function is odd. It's an odd function. It's a function that is symmetric to the origin. Or another way to say this, when you do f of negative x equals f of x, and we talked about this in class, you know, like f of negative, the evenness and the oddness, it's like the spit or swallow, the negatives, and the cosine function, on the other hand, is even. So I think this is a pretty cool connection. So I think this is a pretty cool, another pretty cool connection between even and odd from pre-calculus, and I think this is seen on the Taylor and polynomial series, Taylor-Maclaurin series rather. All right, example 5. Write the nth degree polynomials for sine x and cosine x centered at c equals 0, but in this case using summation form. And then for example number 6, let's use a quadratic polynomial to approximate the value of square root of 1.06. Number 1 centered at 1, and rather letter A or letter B centered at c equals to 0. So I would like to stop the video here, so you might want to try these two exercises yourself and see the solution in the next video.